Welcome to Daily Papers, the podcast where we break down fascinating new research into bite-sized pieces.
Today we're looking at a paper with a fantastic title, Stroke Lesions as a Rosetta Stone for Language Model Interpretability.
I love that. So the Rosetta Stone helped us decipher ancient Egyptian hieroglyphs. The suggestion here is that brain damage from strokes could help us decipher what exactly?
The inner workings of artificial intelligence, specifically large language models, or LLMs, the kind of AI that powers things like ChatGPT.
Right. We all use them, but I've heard they're a bit of a black box. We know they work, but we don't always know how they work.
Exactly. That's the interpretability problem. We can test if an AI gives a good answer, but we can't easily peek inside to see its thought process. The current methods for checking under the hood are a bit like judging a cake just by tasting it. You can say this is a 9 out of 10, but you have no idea what the recipe is or how the chef made it.
So we need the recipe. The paper argues that to truly understand an artificial language system, we need to compare it to the only system we know for a fact genuinely understands language, the human brain.
And not just a healthy brain. The researchers looked at brains that have been damaged by a stroke, which can sometimes cause a language disorder called aphasia. For over 150 years, neuroscientists have been mapping these injuries. They know that if you damage a specific part of the brain, what they call a lesion, you get a very specific type of language problem.
So they're not just guessing, it's a causal link. This damage causes this symptom. That sounds like a really solid foundation, a ground truth as the paper calls it.
That's the key. So the researchers built a framework called the Brain LLM Unified Model, or BLOOM. It's a really clever 3-stage process.
Okay, walk me through it. What's stage 1?
First, they built a model using data from over 400 stroke patients with aphasia. They taught it to do something amazing, to predict the location of a person's brain damage just by analyzing the types of language errors they make.
So, for example, if a patient sees a picture of a cat and says dog, that's one type of error, a meaning or semantic error. If they say dat, that's a sound or phonemic error. And the model learns that these different mistakes are linked to damage in different brain areas?
Precisely. That's the foundation. Now for stage 2, they turned to the AI. They took a large language model and basically gave it a virtual stroke.
How do you give an AI a stroke? You don't hit the computer with a tiny hammer, I assume.
No, it's a bit more elegant than that. They systematically disrupt parts of the AI's internal network by adding digital noise. They call this perturbation. They did this to many different parts of the AI at many different levels of severity, creating thousands of impaired AIs.
And then stage 3 must be the comparison.
Yep, they gave these impaired AIs the exact same language tests that the human patients took, things like naming a picture or completing a sentence.
And this is the Rosetta Stone moment. They took the error patterns from a broken AI, like it saying dog for cat over and over,
and fed those errors into the model they'd trained on humans. That model then generated a map of a predicted brain lesion. It answered the question, if a human made these exact mistakes, where would their brain likely be damaged?
That is brilliant. So the final crucial step is to see if that prediction is accurate. Did the AI break in a way that looks like a human breaking?
It did, and the results are kind of staggering. The predicted brain lesions based on the AI's errors corresponded to the actual brain lesions in similarly behaving humans far, far more often than you'd expect by chance. We're talking in about 67% of cases for picture naming and over 68% for sentence completion.
Wow, so there's a real systematic alignment between how the AI fails and how the human brain fails.
But it gets even cooler. Neuroscientists have a well-known model of language in the brain called the dual stream model. To put it simply, there's one brain pathway for processing meaning, called the ventral stream, the what pathway, and there's another for processing sounds and grammar, called the dorsal stream, the how pathway.
The dictionary versus the pronunciation guide.
A perfect analogy. And when the researchers looked at the AI's errors, they found that when the AI made meaning-based errors, semantic errors, the model predicted damage to the brain's ventral stream, the what pathway. When it made sound-based errors, phonemic errors, it predicted damage to the brain's dorsal stream, the how pathway.
That's incredible. It's not just making random predictions, it's respecting the known functional map of the human brain. Okay, so this is obviously a huge deal for brain science, but what does it mean for the future of AI?
It has huge implications. First, it gives us an external, biologically grounded way to test our understanding of how AI works. If we have a theory about what certain part of an AI does, we can now lesion it and see if it produces errors that map onto the correct part of the brain. It's a way to validate our theories.
So it helps us finally write the recipe for that cake.
Exactly. Second, it could help us build more efficient AI by figuring out which parts of the AI are critical for certain functions, just like critical brain areas. We might be able to prune the non-essential parts, making models that are smaller, faster, and less expensive to run.
And the paper mentioned a more futuristic idea, something about digital tweens?
Right, this is looking further down the road, but imagine you could create a digital twin of a patient's brain lesion inside an AI. You could simulate their specific language problems and then test thousands of different therapy strategies on the AI model before trying it on the actual person.
That would be a game changer for clinical neuroscience. So by looking at the very human process of how language breaks down after a stroke, we found a key to unlock the black box of AI. The Rosetta Stone really was the perfect metaphor.
It really was. It shows that even as we build these incredibly complex artificial minds, there's still so much to learn by looking at the biological one that inspired them in the first place.